Today our new topic is on coastal littoral processes. In this topic, our focus is on the segment of the coast with active marine processes, which is located between the offshore breaking point, where shoaling waves begin to move the sediment, and the onshore limit point, where is usually delineated by a dune field or cliff line. So the emphasis is on this particular section, for example, a sandy beach, where sediments continually respond to direct wave action, wave-induced littoral currents, currents induced by the wind and the tide, and also wind itself. Of course, if this segment of the coastline is not sandy beach, it is not rich in sediment, then what we discuss in this topic will not be applicable, because we will also be looking at a different type of coastline later, whereby we can have sandy beach, we can have muddy beach, and we also may have rocky beach. So as we just mentioned, what we are seeing here now highlight the coastal littoral zones, whereby the seaward limit is at the wave breaking point, and the landward limit is at a dune or cliff. Now, as wave enters into this region and begins to break, that's where the wave energy is now concentrated and interacts with the sea bottom, as we mentioned. So this interaction allows the incoming wave to churn up the sediment and bring them shoreward. Of course, as the wave dissipates its energy and run up the shore, it can push some of the fine sediment into the shore, but the backwash will actually bring most of the sediment back into this region. Now, under normal weather condition, we define this as the limit of the sediment transport, because it is less likely for the sediment to be able to go beyond the breaking point, although that might happen in severe storm events. Likewise, under direct wind action, the shoreline here, the land part of the shoreline, will also experience sediment loss, but typically the sediment transport will be stopped by the vertical dune or cliff over here. Again, in severe event, of course, the wind may also actually transport the sediment beyond this particular limit. So what we are defining here is the limit of the littoral transport, the littoral zones under regular weather condition. Now the transport in this direction, due to the wave primarily, is known as onshore-offshore transport. So onshore transport bring the sediment in, offshore transport bring the sediment out. Now meanwhile, we'll also have longshore transport, which is the transport perpendicular to the plane, perpendicular to this figure, which is along the shoreline. And we will look at both of these components in more details later on. So by definition, littoral zone is the zone where littoral transport occurs, and littoral transport means the movement of coastal sediment. Meanwhile, the sediment itself, the material, is known as littoral drift. Erosion is the net loss of sediment from an area, whereas accretion is the net gain of sediment in an area. So in this particular topic, our interest will be to look at the engineering side of the problem, such as what is the trend of this littoral transport over long and short term. How far does the sand or the sediment move in a seaward direction? What is the net direction of motion in a particular coastal area? What is the average shape of the beach profile? What is the effect of proposed structure on littoral transport, and so on. Here we are looking at the coastal zone. Again, in this figure, we have the offshore region, the shore face, the foreshore, and the backshore. The foreshore and backshore make up the beach, which is limited by the dunes on the land side. We have berms here. We have the high watermark and the low watermark due to the tides. And as you can see, that mark the region of foreshore, whereas the offshore and the shore face region is demarcated by the breaking point, as we mentioned earlier. So essentially, the offshore and the shore face, these two sections, they are always below the low water mark, which means they are always submerged in water. But more specifically for the offshore region, it is where the wave orbital motion does not fill the bottom. This is where we define as the deep water area previously in wave mechanics. There is an imaginary line here known as the fair weather wave base, below which the water column is unaffected by wave motion under normal weather conditions. And since the orbital motion does not interact with the seabed, so there is no littoral processes in the offshore region. The littoral processes only begins at the breaker point here, onwards up to the dune. Of course, this is the limit under normal weather, as we mentioned previously, whereby in a severe storm, large grains size can still be transported beyond the breaker point, whereas during normal situation, sediments which are in suspension may also possibly goes into the offshore region. From the offshore point or the breaker point, if we move landward, this is the section where the wave now begins to fill the bottom. And as a result of that, the shear effect begins to move the sediment particles to form uniform and periodic ripples on the seabed. These ripples will have crest, which is parallel to the wave crest. And because the wave begins to interact with the bottom, the sinusoidal profile begins to be distorted. This causes the crest to have a higher forward velocity, whereas the trough to have a smaller rearward velocity. Because of that, we get a net forward motion, not only on the water surface, but also in the water column as well. And since the orbital motion goes all the way down and interacts with the seabed also experiences a net forward motion, which causes the ripples that form on the seabed to move or propagate slowly in the same direction as the wave. The surf zone is basically defined as the zone which comprise the shore face and also the foreshore, where the waves are active. And this is the region where there is significant onshore-offshore transport, which may be attributed to the effect of shoaling, wind-induced surface drift, wind-induced setup, current induced by irregular bottom, rate current, and density current. So as the wave orbital motion begins to fill the bottom, they churn up the sediment and begin to transport them landward. When the waves become increasingly distorted with high wave steepness and it eventually breaks, it dissipates most of its energy right here, and as a result, the sediment which has been carried will be deposited in this region, forming a sandbar. The broken waves will still have some residual energy, So it will continue to carry some of the finer particles into the foreshore region. And this particle will be washed up the beach. The finer ones may be deposited here, but the majority may still be washed back down up to the sandbar here. The shore face zone can be divided into a smoother lower part due to the back and forth movement of the wave, whereas for the upper part it is characterized by the sandbar, which is formed due to wave breaking, as we mentioned. In the beach area, we have the foreshore and the backshore. The foreshore, as we mentioned, is located between high and low water mark, which means that it is shifting on a daily basis, but basically within this region. It's called the swash zone because this is the area where the residual wave energy run up the shoreline, depositing some of the fine sediments and then backwash into the sea again, carrying most of the sediment. Backshore, meanwhile, is characterized by the dunes and the berms. They are formed from the wind-transported sediment.